Hello, my name's Chase Dehan. I am a data scientist at Progressive Leasing in Salt Lake City. And today what I'm here to show you is a new package. This is actually the first time released to the public, but it's on a feature selection algorithm that is largely based in spirit similar to the Baruda algorithm. So basically just about where it is that we ran into a problem like many other people do where we have a large subset of variables and we're trying to select it down into a reasonable number and get better model performance. So there's a number of other methods, but none of them were really working to fit our purposes very well. So built my own, very similar to Baruda, and then thankfully my employer allowed us to open source it, so it's available, and you can now, it's as a package, so you can now pip install it. And so basically what we're looking at is a generalizable feature selection model that we can apply to a wide variety of different topics. So just about me a little bit is that I am a data scientist, as I was saying. Prior to my current role, I was a finance professor at the University of South Carolina Upstate, and I did my PhD in economics at the University of Utah. And most of my interests more recently are in building the automated machine learning processes. So this is one step. There's a number of other things that I have going on that I'm trying to build for an entire pipeline. So basically, just in a little bit more about Progressive, that's obviously who I work for, and I have to give them a shout out and say thanks for letting me open source this package. Basically, we are a wholly owned subsidiary of Aaron's, and we are the largest virtual lease to own. So that's basically you walk into a retailer. So our biggest retailers that we have are Mattress Firm. We have a number of jewelry places, as well as Big Lots are a couple of our big retailers. And it's basically we are a tertiary lender. So if a lot of our customers don't have a credit card, so they will step down into our space. So we do a lot of credit risk modeling. We have a full team of data scientists and engineers. And underneath a lot of the credit risk modeling, we have to figure out how much we need to give, how much money we're going to give our customers, whether to approve them or deny them, as well as identifying fraud. Because in our line of business, there is a large amount of fraud that we have to try to weed out. And then more recently, over the last year, we started working on optimizing our collections, so such as finding what time of day to call somebody or what time they're most likely to repay us, as well as trying to optimize some of our sales channels. All right, so the motivation behind a lot of this, right, was because we're doing a lot of credit risk modeling. We have very large feature sets. We call a number of different credit bureaus that have a number of different attributes, and we try to reduce a lot of this down. So Baruda, just a show of hands, who here is familiar with Baruda? Okay, not very many. So Baruda was built on top of a random forest, and it tends to work very, very well with a random forest. But some of the newer algorithms, such as XGBoost and other boosted tree algorithms, don't really work well with the random forest, just because of the size of the tree that you can build off of it, right? So, right, with a boosting algorithm, you're not typically going to build as deep of a tree, so you're going to have a different potential subset of features to use. So we built this wrapper specifically tuned around XGBoost. And just about, basically I'll show you about on the algorithm right now. So when we look at some of it, there are a number of other methods. And I'll just give a quick overview about why it is that we're looking at some of these other aspects. So for example, on the bottom, what Baruda typically will do is it will create a subset of shadow features. So it'll create a random, it'll take your X data frame, right, and it will shuffle all those features, and then it will look at the feature importances on that random forest, and it will sort them, as you can see on this plot here, to the important, tentative, and not important. And so you see on that particular plot, All the green features are ones that you would want to keep into your model, which that works, as I said, very well with a random forest. Okay, when we look at the lasso, right? So if we're looking at a regularized linear regression, is that way it helps us decompose our variables specifically down to 0, so we get those 0 coefficients off of it. The problem that we have with that is we use a lasso for variable selection is when we put that into, say, something like XGBoost, is that you're not going to be able to capture some of the nonlinearities between the variables, so there might be interactions that you might not have explicitly stated inside your model. And so these other tree models can't pick those up, right? And so we're going to miss out on some of those. So it might look, in a lasso, it might look not very important at all, but it actually might be really important. It might have a really strong interaction with another variable. And then there's a number of others like PCA or PLS that will give you some other ranking algorithms. But a lot of them run really, really slow. Some that I typically like that seem to work well. So recursive feature elimination. Anybody here familiar with recursive feature elimination? Right? Big problem with that one. It seems to work really well. It's basically you run the model and then you delete a variable and then you check and see if that helps and then you keep going down. That can take forever to run. And so this approach basically says, hey, we can do this much, much faster. So the next thing you need to talk about here, just briefly, is a common way that we do our feature selection. And if I am speaking pretty fast, please feel free to stop and ask me questions. But typically, one of the things we're looking at here with regard to feature selection is we'll take our first step and we will run that feature selection algorithm over the entire data set, right? And so you say, in that step first, we take and dump all our data in there and we spit it out and we say, all right, these 50 variables are going to be important in our model. And then we run it through the cross-validation, right? And so then we evaluate on those holdouts, on those red sections that we see there. But this is a wrong approach. Anybody know why? Right, we're overfitting, right? So what we end up seeing, right, is that because we were setting it up off of that portion there, right, where we have that part is that we did the feature selection, that data has already been seen, okay? That data has already been seen, so we can't use that just right there at the front end of it. So the right way, this is one way you can do it if you have a smaller data set and you're not able to create a true holdout. Because of course, if you create a true holdout, then you can evaluate it and you'll be fine doing that. But the right way here is that we do this nested cross-validation where we have inside each fold, then we do our hyperparameter tuning as well as our feature selection on the inside there. Okay, so that is one caveat that we need to make sure is aware. Okay, so now I'll actually get into talking a little bit more about what the algorithm actually does, because the algorithm itself is actually surprisingly simple. The entire package, when I first wrote it, it's only about 120 lines of code. It's pretty short, but one of my opinions is that simplicity actually sometimes ends up working much better than complexity. So I'll go through here 3 different ways. The first way, I'll walk you through the steps on this part, then I'll diagram it, and then I'll actually show you the code, so hopefully you can understand what this is. Because at the end of it, I would really appreciate any feedback that anyone has. This package is up on GitHub, and I'll show you where the link is to that as well. So basically, what we're doing here is that we take in an X data frame. Okay, and then what we do is that we take all of those features, say we have 100 features, we take all 100 features, and then we randomly shuffle those features, right? Because if we randomly shuffle that feature, it shouldn't actually have any impact on our Y, right? It shouldn't have any impact because it's just a random order. So after we do that, and we call those shadow features, and I take this term from Baruda, is that what we do at the next step is that we run XGBoost over that entire new data frame. So if we had 100 features, now that has 200 features, and then we run the XGBoost on that entire thing. After we do that, we then run it 10 times just because there is some random variation, because sometimes that tree will split off of a random subset of features. So then we collect the feature importance value off of each of those features after it runs through XGBoost. Now this is a really simple metric. It's how many times that variable has actually been split on, right? So it's a really simple metric. It's not looking at any other aspects. It's just simply put, how many times in that XGBoost run did it actually get split on. And then, let me see what's stepping on out. And then the next step is we want to compute a cutoff, right? So we want to figure out which variables should we be dropping out of this data frame. And so we create that cutoff by taking all those shadow features, and then the default parameter here is 4. So we average all of the shadow features, importances, and then divide it by 4. That is a parameter you can actually change, but 4 is a pretty good one to use in there. And then we remove all the features that are below that cutoff. And then we iterate again as long as we are removing above that certain threshold, which the default parameter here is 10%, and you can alter that if you like. But that will actually allow you to remove, like, so if you only remove 3% of your features, if like you have 100, right, and you only delete 3 out of it, it's not going to run through another iteration. But if you delete half the features out, it says, all right, let's run this. So you have to delete at each step, at least above that part. And at the end, it spits them out. So here is the actual sort of diagrammed out. You have to pass in a data frame here that is one hot encoded, right? Which basically just means we take that feature. So if we have state, which is say California, Idaho, Utah, it says state California 1 or 0, state Utah 1 or 0, right? And so we have the data frame running through that way. Sorry, the question? You have to do that beforehand. And I'll just show you. So because we actually have to pass in a pandas data frame, so there's a just really easy function, the pandas or pd.getDummies. And I'll show you a demo at the end about how to actually do this. Yeah, so then we shuffle the features. And one thing that this diagram doesn't do a very good job on is on the shuffled features aspect up there, is that it's randomly shuffling on each column. It's not just shuffling them according to, it's not keeping the same order for each column. I hope that's clear. Right, so then we combine it, and then after we run the XGBoost on it for those 10 iterations, we split back out the shadow features as well as the regular features on it, and then we're comparing that to the cutoff. And so then, following it over to the right side of the slide, we're saying, all right, are these variable importances above that 0.5, that threshold that we determined off of looking at all the shadow features? And we remove that variable, and then we iterate through again. Okay, so I will quickly show you what it actually looks like.
I've got a question.
Shoot.
So you make a copy of your data frame, and then for each column, you randomly just shuffle the values in that column?
Yes.
Okay. And you do this so that you basically like decorrelate all the information.
Correct.
And so then you find out how important like the noisy feature is. That's what your sort of baseline is?
Right, yeah. Because
then you compare the actual features splits to that baseline to see if they have any information in them.
that is correct. Yeah, so we take each individual feature, and then because there shouldn't be that relationship between these shadow features and the actual, like the variables that we want to keep in our model, but some of those variables that we randomly shuffle will be just noisily just correlated with the target variable. So yeah, so we're just comparing those two there. And I actually can't see my code on the screen. Sorry, 1 second here. Oh, man. Okay, that might be a problem. maybe I can just try and pivot over here a little bit. So basically, the way it works is that we have it's set up in a manner that we can similar to the SK Learn classes. So we're going to there is some parameters in here that we do some error checking on, but you basically have a fit, a transform, and a fit transform on there. Let's see, so let's see over here. All right. Can you guys see that at all? I'll just show you guys just directly on GitHub. That'll probably might be the easiest way to do it. So I've had that issue in the past. My apologies. All right. All right, well, I am going to, my internet connection as well is not working now. So I'm just going to carry on with this and I'll try and come back to it at the end. If you guys are okay with that. So. All right, so I'll just quickly show you what the results end up looking like. Basically what we did is we did a 5-fold cross-validation on it and predicted on the out of folds. And then repeated the tests 5 times and tested it on a number of different data sets, mostly coming from the UCI machine learning repository. And the data sets it seemed, at least from my initial testing, that seemed to work really well on are binary target variables, so just a 0, 1 target variable. Some data sets on the multi-class are not, at least some of the testing are not, it's not showing as high of performance on it. So this is the basic testing methodology that I use when running the tests. And what the results actually look like, this is running back-to-back. This is running on a 12-core Linux i7, or 6 cores, 12 threads. And basically, so when you look at these 3 data sets, which were all 0, 1 target variables, Boosteroota outperformed, at least according to log loss, on each of these data sets. A couple of them highly outperformed. One of them, which is the second, that HR data set, Boosteroota does not perform as well as Boruta did on the log loss metric. But what you can see is that it is substantially faster if you look at the Boruta time in seconds versus the Boosteroota time in seconds. So that's what we end up seeing with regard to the actual the results and the timings on that. So the actual usage of it it's pretty simple. You can just pip install it. I am planning on having an R package available, and I know in the description for this it said it was going to be an R package, but I started building this in Python instead. So there's a couple of features that I'm planning on adding to this over the next few weeks, a couple months, and then after that point, once I have everything stabilized on it, then I will start working on it as an R package. But it's pretty straightforward. And can you guys see that slide? Okay. Well, all of this stuff is also on the GitHub as well. So I guess I'll kind of explain it to you there. So basically, can you guys in like the middle of the room see it? Yes? Okay. All right. But the back, you guys, it's kind of small? No? Okay. All right. Right. So this is just showing a very simple way to do it. So we're just going to import it, right? So from Boosteroota, import Boosteroota. And we do have to pass it in as a pandas data frame. So the first step that we see as on that step is that we one-hot encode the variables. So we take that x, we do the pd.getDummies, and then we initialize the object. So convention I like here, but is the br is equal to Boosteroota, and then we have to actually specify the metric. It will fail if you don't specify a metric on it. So you specify a metric, and you can pass in some of the optional tuning parameters in it. And then what we do after that point is that we fit the x and y off of it. And then we can actually look at that attribute, the keep vars attribute, which will actually spit out a pandas series and tell you which variables you have. And then you can use that inside your brackets when you're just extracting them out of your data frame. And then the last part you can do as well is if you want to actually have it drop the variables for you, you can just use the transform method off of that x. As I said, there are a few tuning parameters, and I apologize if these do end up coming out small. But it's basically we have the cutoff where we can change the cutoff value that we have for like how aggressive we want to actually drop variables out of it. And then we have the number of iterations. So if you're dealing with a much larger data set, you might want to have a lower number of iterations for each loop that it runs through. And then we have our max rounds, which is the max number of times you want to iterate through. And then the delta is a stopping criteria for determining what percentage we want to allow in. So we could have, you can set this as low as you want to basically just let it keep iterating through until it hits, basically until it stops deleting. All right, so I'm going to show you a demo, and I'm going to try and make sure it actually works here. Or I can show it to you. Where am I at? Man, damn it. So this is available on the GitHub. Unfortunately, I don't know how to make it look bigger. Yeah. So I can't see on my screen. Sorry. Go to what? Oh, it doesn't work. Control Shift A. No. I don't know. My Zoom doesn't seem to work, but it works on everybody else's PyCharm. So I'm just going to run it, even if you can't see it. And then I'm happy to show anybody individually if you want to see it. And this actual demo as well is on the GitHub, and I'll try and get that shown to you as well, at least at the end. So basically what we're looking at here is that there is a data set here that is downloaded from the, so it is downloaded from the, directly from the UCI repository. And then you have on the step, we initialize the booster root object, and I guess I need to download it. And then so what's happening right now is that at the top of the script, and you can look at it, is that it's pulling down the Madelon training data set, which was actually used in the original Baruda paper. And then and just to show you on this, in this actual data set, they were showing on Baruda on a single core was taking 9 hours. And I'll show you what happens here when we fit it. Is it's actually running, and this is just an i7 that I have running on here, and you can see it's already finished. So it's running much, much faster than the Baruda on the same set. It's also performance is substantially higher. And so basically as we look through it is that we fit, we transform, and actually my internet, and I can show you now, now I will show you what the, so on the actual repo, you can see there's the ODSC West folder in the repo, and you can actually see the demo that I'm trying to show here. And so, can you guys see that code at least? Yeah. All right. So yeah. So you can actually you can try this yourself if you want to, but this is just prepping the data on the first step, and then the next step down here, right, is that we are just initializing it, and then we fit, and we are then looking at the length of it, and then we have the transform, which will create the new training data set that we have the reduced set. And then we also have the fit transform, which will do the fit and the transform in one step if you just really don't care about what the intermediate step is there. And then there's just a print there at the end. Now I do have a little more time. You guys interested in seeing the code for the actual algorithm? Okay, cool. All right, and is that visible? All right. So basically, when we start it, is that inside the class when we are fitting it, we will come into the boosteruta method here, which then comes through, and basically we have the loop here, which basically is looking for the criteria, and it calls actually out to the function up here, the reduce vars, which actually goes through, and you see it running down through here, is that we fit the parameters depending on what gets passed in. We then create the shadow variables here, which calls out to the other function, which then randomly shuffles each of the values. And then through the bottom portion is we are finding the importance, and then down here is that we are then looking at the criteria to see if it actually is looking at that delta, and then it returns back the stopping criteria and the variables that we want to actually keep inside the model. But that is basically the general part of the algorithm. Are there any questions on the algorithm that I can answer for you? Yeah.
You're just using like the default parameters for the XP boost, and can you like specify if you have?
So yeah, right now I'm just using default parameters on XGBoost. I did try to initially put in some tuning parameters, but I didn't see much of a change in the actual, like, obviously there's a change when you're trying to on your final model, but actually for the feature selection algorithm, it didn't actually make a difference. And just to be clear, the question there was, we're just using the default parameters in XGBoost. One of the things I do need to change in there is the n rounds, because n rounds default parameter is at 500. And so if we're dealing with a really wide data set, then it's going to, you know, it's might just randomly end up dropping more features than we are. I've been able to run this through with about 22,000 features, one hot encoded features, and runs, you know, much faster than Baruda would. One example set that we had, we trained this on, it took about 2.5 minutes versus about 8 days on Baruda for a similar training set. So what I'm working on for the future, and if anybody has any interest in helping me out working on this stuff, I'm greatly appreciated. But I'm going to be working on the R package. XGBoost also has some nice GPU functionality, so I'm wanting to put that in as well as passing in PySpark. I would also like to look into also using LightGBM, which is a very similar algorithm to XGBoost, but appears to be running even faster. So that's basically all I have. Is a little bit on time, but I would appreciate anybody, if you do like it or use it, is to please go and star it on GitHub. Send me feedback, especially if you use it and something breaks. I'm really interested in all that. And there's my contact information in there. I'm happy to take any questions you might have. Yeah.
How is it different from PCA? I think you have already explained that, but I'm asking that question again. And how is the importance of a variable is determined? I saw the code and it was F-score, I guess.
Yeah, so the F-score is directly comes out of XGBoost, and the F-score out of XGBoost is purely based off of the number of splits, like the number of times that variable is split on inside that actual model.
Can the metric be changed to cumulative variance or something like that stuff?
Not inside of my algorithm, but there are a number of other other importances that you can pull out of XGBoost. This one just seemed to work the best for what I have. So yeah, and then as far as the question about PCA, you know, PCA is looking at like linear relationships between the X and Y, whereas this one is a wrapper around XGBoost. Okay. Any other questions? Yeah.
Any thoughts to expand this beyond XGBoost to make it more model agnostic? Not just
I would like to, and that's one thing I'm going to start trying to play with LightGBM, but one of the challenges is about how we look at feature importances. That's actually a big challenge, is many different models have different importance features, and I haven't come up with a good way to do that. So.
I haven't either. I was talking to Data Robot
Okay.
yesterday, and they said they had some way to do feature importance regardless of model.
Okay. Yeah, I don't know. I'm not sure on that. Any other questions? All right. Awesome. Well, thank you guys very much. Please start the project on GitHub, and